Okay, in this video I'm looking to go through the C3 2016 paper, so hopefully if there's any parts that you're stuck on you'll be able to have a look at this and see how it would be answered if you can't really grasp it from the mark scheme and what have you. Right, so we'll get started. Okay, so first question is 3 differentiation questions, and they're all 2 marks each, different format for the answer in the second one, but see if we can answer all these. So bear in mind I am using a mouse to write these answers out. It's not the ideal situation for this, but hopefully it won't look too bad. Okay, so we're starting off with y equals 4x plus 1 all cubed multiplied by sine 2x. We're asked to find the derivative dy by dx. So first thing to notice in this is that this part is multiplied by this part, which tells me this is going to be a product rule for this one. So we can call this u and we can call this v. And the product rule for this is going to be u times v dash, or this part differentiated, plus v times u dash, which is v times this differentiated. And I'll just write that out so we've got all the bits and pieces that we need for it. So I'll just write down which question this is as well. So u is our 4x plus 1 all cubed, like that. And our derivative for it, our du by dx, or u dash, is this part differentiated. So for this you're going to need the chain rule as well. So the chain rule for this means we differentiate the outside part of the function, that is this cubed, and multiply it by the inner part of the function differentiated. So what will happen is this 3 is going to drop down to the front, and what's in the bracket remains the same, and we get a 2 up here. So we've differentiated the outside. The inner part differentiated, well, the derivative of 4x plus 1 is just 4. So this entire thing we're going to multiply by 4, and we end up with 12 lots of the bracket inside there. For the v part, v equals sine 2x, and v dash is then 2, 2 comes out from the chain rule, and then we have cos, because sine differentiates to cos 2x here. And this is a product rule, so it's this multiplied by this plus this multiplied by this, and we get this lovely product symbol there. So all in all, we have that dy by dx, or y dash, y prime even, is equal to 2 lots of 4x plus 1 all cubed times the cos 2x. Just put this 2 over there, makes it look a little nicer. Plus 12 lots of 4x plus 1 all squared multiplied by sine 2x. It's not looking for anything else. It's just after the derivative, so we can move on to the next question. Okay, so our next question is, given that, show that dy by dx is this. This is going to be a quotient. We've got a divide sign, well, just a line in it generally, so that generally dictates use the quotient rule, but we've got one function divided by another. Now, in the formula booklet, the quotient rule is there. It's given in a very weird format with these g of x's, f of x's, dashed and not dashed and what have you. But if you ignore the x's, you could basically call the top thing f, the bottom thing g, and follow that rule as you go on. So for this one then, this top bit here, I'm going to call this u. And the bottom part I'm going to call v. And we can just work this out. So u is 2x squared plus 3. That means that u dash is 4x, and that's it. The 3 disappears. We're good. V is equal to 3x squared plus 4. So v dash is 6x, and we're done with that for our workings. Right, so now what we're going to need is we're going to need to look up the quotient rule. So quotient rule for this is v u dash minus u v dash all over v squared. Right, let's write it out then. So we end up with 3x squared plus 4 multiplied by u dash, which is 4x, minus u v dash, so that's 2x squared plus 3 multiplied by 6x. So as we can see here, it looks like 6 and 2, that's going to give me 12. 4 and 3, that's also going to give me 12. And there's not going to be a quadratic term on the top there. This is all over v squared, which is 3x squared plus 4 all squared. And that is what it wanted on the bottom there. So general rule for quotient rule, it's not wise really to open up this bottom bracket. So just leave it be really. It's the best thing for that. Okay, so let's open up these top brackets, because then we can simplify it down to just px. We'll find p in the process. So first off, we end up with that 12x cubed, and that's going to disappear in a moment, plus 16x. Now this entire term here is going to be negative, so that's negative 12x cubed. Oh look, that's just going to vanish. Plus, no, that's going to be negative. It's all negative because this thing here at the front, that's going to be minus 18x. And that's all still over 3x squared plus 4 all squared. All in all, that's going to cancel with that, so let's just drop them out. 16x minus 18x, well, that's just minus 2x. So we have negative 2x on top for our numerator, and 3x squared plus 4 all squared for the denominator. That's that one done. Okay. The next one then, given that y is equal to the natural log of this, find dy by dx. Now, it's a little bit suspect that everything here is in this bracket here. So, whenever you differentiate a logarithm, you get 1 divided by whatever's in the bracket multiplied by the derivative of what's in the bracket. That's how a chain rule with a logarithm works. So just to kind of give a quick example of that, say you needed to differentiate ln of 3x, you instantly get 1 over whatever's in the bracket, so 1 over 3x, and then you multiply by the derivative of what's in the bracket, so standard chain rule, and that ends up being 1 over x. Now that's just to kind of give an example of what's going to happen with this one up here. So we started off with y equals a natural log of what was in that bracket, and I can't remember it, 2x squared plus 3 over 3x squared plus 4. Let's double check that. Looks okay. Right, so the derivative of this is going to be 1 over whatever's in this, so bear with, because this is going to look absolutely horrid. 1 over 2x squared plus 3, which is also over 3x squared plus 4. And if you've got to this point, you're probably thinking that's not a disaster so far. I've got a fraction within a fraction. How do I get out of it? To be honest, it's not too hard. What I'll do is, instead of doing that, if we want 1 over this here, that's the same thing as just flipping the entire fraction around. So, for instance, if you've got something like 1 over 2/5, the answer to that, you can type it in a calculator to check for yourself, is 5/2. It's literally just flip what goes on the bottom. So that's what I'm going to do. I'm going to just write 3x squared plus 4 over 2x squared plus 3. So that's the 1 over part here. I now need to multiply it by the derivative of the inner part, which I just so happen to have here. So that's what we're going to do. We're going to take this guy and we're going to multiply those two together. Right. And we're pretty close to the end of this now. It's not asking for it in a particular form, so I'll just write it as minus 2x 3x squared plus 4 divided by 2x squared plus 3, 3x squared plus 4 all squared. I'll need to check the mark scheme in just a few moments to see if that would give you the full marks for it. But what you can notice at this point is that you've got 3x squared plus 4 on the top. You also have 3x squared plus 4 all squared on the bottom. So you can just cancel that a little bit. It's not going to cancel fully because this numerator part isn't squared, but we can get rid of that. And that becomes to the power of 1 instead. So we just have minus 2x all over 2x squared plus 3, 3x squared plus 4. And that's the first question. Six marks. Question 2 from the C3 2016 paper, and it looks like it's starting off with numerical method style question. We've got y is x to the power of x, where x is greater than 0. It intersects the line y equals 5 at a single point where x is equal to alpha. Show that alpha lies between 2 and 3. So standard method for this is to set whatever you're given equal to the other equation that you're given, and then rearrange that so that's equal to 0. Once you have that, you can substitute in 2 and then 3, and you should notice a change of sign, and that for AQA is enough to show that there exists a root. Of course, both graphs have to be continuous in that interval for that also to be true, but AQA don't seem to care about that. Right, so as I said, set this equal to this, so we have x to the power of x equals 5. Doesn't matter which way you do this now, we can have x to the power of x minus 5 equals 0, or 5 minus x to the power of x. Either one's fine. So what I'll do is I'll just write x to the power of x minus 5 equals 0. Now, as I said before, it doesn't really matter which way you have this, but just to be careful, I've written it in this way. And the reason for that is, when I go to type this into my calculator, I want to make sure that my calculator interprets everything correctly. So if there's a negative in front of this x to the power of x, I want to be perfectly happy that the calculator is going to interpret it correctly. So this way, I'm minimizing the amount of errors that could pop out of this. Okay, so let's sub in 2 and then sub in 3. So I'm just going to call this, let's just call this f of x for now. Save some of my writing. Okay, so I'm going to work out f of 2 for this, and just to be correct, I'm just going to get rid of that 0. F of 2, just subbing in 2 into this equation, that's 2 to the power of 2 minus 5, and what's that? That's 4 minus 5, that looks to be minus 1. Okay, f of 3 then, just getting the 2 and 3 from here. That's equal to 3 to the power of 3, which is, oh god, 3 cubed, 27. 27 take away 5 is 22, I think. I'll correct myself with a calculator in a moment. 27 minus 5 is, yeah, it's 22. And what we have here from these is a change in sign. So we can just write out, let's change that to 12. Change in sign, and you don't need this for AQA, but the graph is continuous between 2 and 3. Therefore, there exists a root alpha between 2 and 3. And that's sufficient for the marks for that. Okay, this next one now. Show that the equation x to the power of x equals 5 can be rearranged into the form x equals e to the ln 5 over x. Right, so there's not many clues in this, but we've got a ln and we've got an e. So if we try getting this ln 5 first, we can do that by lunning both sides here. Well, the reason I'm looking at this ln 5 is that it's the most inner part of the function. So because it's the most inner part, it looks like that's probably the thing that was done first before everything else, like the e and the divide by x, then the e happened. So if we ln both sides of this, we're going to have ln of x to the power of x equals ln 5. Okay, so we've got our ln 5. I'm going to just drop this x to the front of that ln using one of the laws of logarithms. So now we have x ln x equals ln 5. Okay, and now we can get this divide by x that we've been looking for before. So we have ln x equals ln 5 over x. And the last step, just to get this x on its own, we do the inverse of the logarithm here and just raise everything to the power of e. So this logarithm and the e would cancel, and this would be to the e to the power of that. So e everything, and we get this. Results shown. Okay, use the iterative formula x subscript n plus 1 equals e to the ln 5 of x subscript n. Okay, with x1 equals 2 to find the values of x2, x3, giving your answers to 3 decimal places. Now this is important. If I don't do this, I'll get nothing. So, gotta be very careful. Right, sub 2 into this, and I'll get my second value. So, ln 5 over 2, and then e it. So, in my calculator, I've got e to the ln 5 over 2. Let's just type that in. Don't need to be concerned with anything like radians or degrees and that, because there's no trig involved. Answer I get to 3 decimal places is 2.236. Well, the next number after that 6 there is 0, then 6. So I don't need to worry about rounding up or anything. That's sufficient. Okay, x3 then, for this, equals e to the ln 5 over. Now, instead of dividing by 2.236, what I'm going to do is I'm going to use the ants from my calculator instead, just because. And I'm just going to write x2 there instead. Looks like I'm running out of room here a little bit, but we'll see. Okay, ln 5 over x squared, sorry, x2 that should be. Ooh, I've written that in the wrong place. Right, that should be an x2. So, let's go to my calculator. And the answer I get is 2.0539. So that's going to be 2.054. 3 decimal places. That's it done. Okay. Right, Simpson's rule. So you're given Simpson's rule in the formula booklet. Make sure you completely understand how this one works. One thing to be wary of with this one is that the way that the coefficients are multiplied is different to how trapezium rule mid-ordinate work. So for this, the coefficient of the first thing would be 1, then the next one's 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. It always ends in 4, 1, and it always alternates between the 4 and the 2. So for this one, we've got 7 ordinates, so there's going to be 7 numbers put in, and the middle 5 are going to go 4, 2, 4, 2, 4. Right. Let's start by finding the height of these strips. So the height is 1.7 minus 0.5, and that's divided by the amount of strips that we have, so 6. This gives us h, and that's going to be 1.2 divided by 6. I think that's 0.2. Sound about right? Oh, I've done something wrong. No, just typed in the calculator wrong. Yep, that's fine. Okay, so what I can do for my calculator is work out a table of values for this as well. Now this should be pretty clear in the mark scheme as to what those values are, but I'll just write them out just because. So we're going to have our x's here, our y's here, and we make up a table there. So our x values, I'm going to start off with 0.5. It ends at 1.7. The next value will be 0.7 because I add on h onto that. So we've got 0.7 there. Next one is going to be 0.9. And then we've got 1.1. And I've run out of room. 1.3, 1.5, 1.7. So just double checking, I should have 7 ordinates. 1, 2, 3, 4, 5, 6, 7. Perfect. Sub all these in and to this equation here, and I'll get my y values for the formula. Now, the mark scheme for this should have these written out fairly clearly. Oh, gone too far. And there they are. So, we're using these as we go along, but we're going to have a third of h from the formula, third multiplied by 0.2. That's going to be at the front of everything. And we're going to have this value here multiplied by 1. The last value multiplied by 1. And as I said before, everything else gets multiplied in alternating 4, 2, 4, 2, 4, 2. And it always starts 1, 4, ends 4, 1. And that's why they've got the first one on its own, the last one on its own, 4 lots of this one, and this one, and 2 lots of the other ones, the 1.3 and the 0.91, this one here. And we end up with 4.49. That's it. Okay, so our last part of the question then is hence find an approximation to this here. Now this is a fairly weird one, and what I would suggest people do for this one is, especially if they've got a graphing calculator, is to take the graphing calculator and work out the exact integral of that function there and see what they get. Now I don't have mine on me, so I can't do that, but what it will allow you to do is you can compare your answer from above, where you've got 5 minus x for x there, well 5x to the power of x, with this here, and see what the difference is. Pretty much exactly. Given that this is still an approximation, it's still going to be pretty accurate to what it really is. And see the difference. And it ends up being quite obvious then the difference is 6. But we'll get to why that is now. So just looking at that answer there for this is 4.49 that we got, and also noting that it was 3 sig fig. 4.49. So let's have a bit of a play around with this then. If I was to actually integrate this, what that looks like is I could say, well, the integral between 0.5 and 1.7 of 5 minus x to the x with respect to x, that's actually equal to integrating these all separately. So that's 0.5, 1.7 of 5 with respect to x minus the integral of x to the x, same limits, of 1.7 and 0.5 there. And this is what we're trying to find from above. So this is something we know. This is 4.49. This here, the integral of 5 with respect to x between 0.5 and 1.7, is also something we can actually work out. That's going to be 5x when we integrate it, and we sub in 0.5 and 1.7, and we've still got negative the integral that we're trying to find. Just omitting these here, too annoying to write. Okay, so if I sub in 1.7 and 0.5 into this, I end up with 4.49 equals, let's sub that into a calculator, 5 times 1.7, which is 17/2, minus 5 times 0.5, and that's 6. That's x to the power of x dx. So our approximation for this part here is going to be, well, let's remember that this is negative here. So I'm going to reshuffle this about. So the integral of x to the power of x with respect to x is equal to 6 minus 4.49. And we get an answer of 1.51, which is what the mark scheme was after. Right, that's it for the second question. Okay, so this is question 3 of the 2016 paper, and we're given this mod inequality to solve. Now, the usual layout for this sort of question is that they lead you in with a couple of steps, ask you to graph it out, and this makes it a lot easier to do. But as we can see, there's absolutely no scaffolding here whatsoever. It's just said, go do. So what I'll do now is answer it the way that you should go about doing it, so you can guarantee that you get the marks for this. Now, first thing that I'm going to want to do looking at this is graph it. There's no way around this. I want to graph this out. So with your graphing calculator, go to graph, and the first equation, y1, should be equal to x squared, and the second one, y2, equal to abs, because that gives you your mods, and just some brackets around this, 5x minus 6, like that. Now you can graph this out, and in fact what you can do is you can use gsolve on your calculator, assuming you're using the Casio FX74002 or whatever it's called, and you can get all potentially 4 of the solutions for this. I think there's 4, might be more, no, might be less. Let's have a little look. So I don't have the calculator on this, but I can use this to graph it out. So I'm going to input my first graph, which is x squared. There we have it. And our second one is going to be abs, and that's 5x minus 6. And there we go. So we have these 2 graphs here. So let's just zoom in a little bit and see what we've got. Right, so judging from this, we've got 1 crossing point here. Let's just dot that down. We've got another one here, another one there, and maybe we'll get another one with these 2 lines going off into the distance. And we do. There we go. So just so you know, I've dotted all of these, and these are the answers. Now, it's how we get them that's important. So, solving this, best to kind of ignore this inequality for now. We'll come back to it later, and solve it as if we were solving x squared is equal to the mod of 5x minus 6. And this isn't too bad a thing to do. To get rid of mod brackets, all you need to do is effectively square it and square root it, and you get a positive and a negative answer from your mod. So what we're going to have is we solve two equations. The negative one, which is, well, x squared is equal to the negative of all this, so that's minus 5x plus 6, and the positive version, which is x squared, is actually equal to 5x minus 6. So what you should see from this is, well, hopefully, now that you're on C3, is that these are two quadratics, can be solved by setting them equal to 0 and factorizing. And that's not too bad to do. If you've got a graphing calculator, heck, you could use the quadratic solver to solve both of these, and that's it. You've got two solutions for x from this, two solutions from x from that. So this gets us x squared plus 5x minus 6 equals 0. Something that multiplies together to give minus 6, adds to give 5. Let's think. Probably something to do with 6 and 1. 6 and 1. 6 and minus 1. So x plus 6, and that's a terrible parenthesis, x minus 1. That will do it, and we get x equals 6, or negative 6, or positive 1. Do the same for this. X squared minus 5x plus 6 equals 0. And what we get from this is two things that multiply give 6, and negative, add to give negative 5. That's going to be a combination of 2 and 3, minus 2 and minus 3x, minus 2, x minus 3 equals 0. So we can add more to this list now. We've got 2 and 3, which is exactly what we wanted from here. Okay, so we've not actually solved the inequality yet. What we've solved is when it's equal. So to get the inequality, all we need to do is look at this graph and find what intervals that this is true. Now the easiest way to kind of think about this is, when is the graph x squared over, that is bigger than the mod graph here? So just to put some emphasis on this, I'm going to draw some lines in. We're going to have x equals 1, x equals 2, x equals 3, and x equals minus 6. There we go. So we've got these vertical lines put in here, just to kind of make it more obvious. So first off, we're looking between 2 and 3 here. So as we can see here, the red line is always over the green line. So this isn't true between 2 and 3, so that doesn't count. But after 3, because there we've got 3 there, after 3 the green line is always above, sorry, the green curve is always above this red mod. So this is true for after 3. So I can say x larger than or equal to 3 satisfies this in part of the inequality. We know that between 2 and 3 doesn't. So now let's look between 1 and 2. 1 and 2, well, yeah, the green line is always above the mod. So we can say that x is bigger than or equal to 1, but less than or equal to 2. Now, just kind of hint with this is that literally the green curve is over the mod between 1 and 2. So the way I should write this is having x between two things. It's not sufficient enough to say x is bigger than 1 and then somewhere else x is less than 2. Both of them have to be true at the same time, because if x is bigger than 1, well, yeah, it works for this bit here, but it doesn't work after this. And, between 2 and 3, that's still bigger than 1, so you need to be specific with what you're saying it can be and can't be. So, moving on, we've now got this rather huge interval, which is between 1 and 6. And here, this red line is always over the green line. It's a bit difficult to tell, but if you draw a line going straight down, you can see red is over green. Red is over green. Red is over green. So this inequality isn't satisfied between there and there. But after -6, well, before technically, -6, the green line is then always over the red line. Green curve, green curve, green curve. Oh God, I gotta say that. So before -6, so x less than or equal to -6. And those are all the points of the inequalities that we need. And all of this stuff here can be done with a graphing calculator and shouldn't take too long at all, especially if you use stuff like the gsolve button. And that's that. Okay, so this is question 4 from the 2016 C3 paper. And it's not a nice one, to be honest. You got the 4-mark transformations question at the start here, but the second one is so easy to go wrong because there's so many steps in it, and this format it wants at the end is, well, we'll see when we get there. Describe a sequence of 2 geometrical transformations that maps the graph of y equals e to the x onto the graph of y equals e to the 2x minus 5. So first thing to note with this is that both of the transformations that we have are in the x directions. The order of this transformation does matter. If one was in y and one was in x, you'd be fine. Kind of telltale sign that they're both in the x is that both of these things are in the power. X is basically what the power was beforehand. So let's have a look and see what we can make out from this. So for order of transformations, I tend to just remember what the orders should be. We've got x direction stuff should be translations, reflections, and then stretches. Doesn't matter which way reflections and stretches go, but this is how I remember it. And in the y direction, you've got your stretches, reflections, then translations last. So let's have a look and see what we can see straight from here. So the first thing that I'm looking at is the x minus 5 part here. So x minus 5, we're taking away from x, that's a translation, and it's negative, so that means that the actual translation itself is going to be positive in the x direction. That's translation of 5, 0. The second thing to look at then is reflections. There's none. Stretches last. So stretch is in the x direction. again, telltale sign is the coefficient of x for this. Stretch x direction, and the scale factor is the reciprocal of the coefficient of x. So the coefficient of x is 2, the reciprocal of the coefficient is a half. And it's in the right order. Translation first, stretch last. We're good. Okay, so now we're on to the second part of this question, which is 4b. Normal to the curve y equals e to the 2x minus 5 at the point P, defined as 2e to the minus 1, intersects the x-axis of point A and the y-axis at point B. Show that the area of the triangle OAB is e squared plus 1 all to the power of m over e to the power of n, where m and n are integers. Okay, what does this look like? This is one that I graphed out earlier. Y equals e to the 2x minus 5. This is its graph. And, oh, didn't mean to do that. It's fairly zoomed in at the moment. We've got, 0 to 3-ish here and 0 to 3.6-ish there. So what we're going to have is a normal at point 2. So somewhere here we're going to get this line which is at 90 degrees to the actual curve itself, going through it at point 2, and we're going to get a triangle. We're going to get point A on the x-axis and point B on the y-axis and O there, and we're going to have an area for said triangle. So let's make that normal. So the normal way to make a normal, no pun intended, is to first come up with a gradient for this function here, so we know we can get the negative reciprocal of that gradient to that point, which gives us the gradient of the normal. So if we know that y equals e to the 2x minus 5, then the derivative y prime is equal to, and we're using the chain rule, bringing the 2 forwards, we've got 2e to the 2x minus 5. If I sub 2 into this, I will get the gradient of this curve at point 2. So I'll be able to work out what that slope gradient is there. Right, so if I sub in 2, I get, so y prime evaluated at x equals 2 is 2e to the power of, well, 4 minus 5, which is 2e to the minus 1. And just for ease of writing, I can rewrite this by using this power up here to make that look like 2 over e to the power of 1, or just e. And you can type it in your calculator just to check, what e is. E is literally just a number. It's a very fancy number. It's transcendental. It's irrational. It's 2.728 whatever to the rest of it. So effectively what we have here is 2 divided by a number that's a bit bigger than 2. There's nothing much fancier about it than that. So that is the gradient of the tangent. The gradient of the normal, which is what we want, is the negative reciprocal of that, so minus e over 2. And just because we wrote it like that, it was easier to flip it, like that. Okay, so let's come up with our normal equation. So our normal uses point P and our gradient that we just found. So we end up with y minus e to the minus 1, or 1 over e, and that's equal to negative e over 2 x minus 2. Okay, so that's our normal. Let's write it in. Okay, so for this part then, we have y minus 1 over e is equal to negative e over 2 bracket x minus 2, and there we have it. We have got our normal, and you can see here that, yeah, that's looking relatively 90-degree-ish. That's good enough for me. Let's plot some points down. We've got point A on the x-axis, so we're going to call u point A, and actually I'm going to redo that one because I missed the x-axis, and point B here. Right, so what are they? So obviously I've got what those coordinates are there, and that's what your graphing calculator would give you as well if you plotted this in and wanted to G-solve it and what have you. It wants it in exact format, so I can't use any decimals in this. That's going to be useless. So if I want the x-axis, point A, now let's use a fancy color. If I want point A, that is when y is equal to 0, but I don't know what x is. So let's work out the normal. When y is equal to 0, we get 0 minus 1 over e is equal to negative e over 2 x minus 2. So because we've got that 0 there, I'll just get rid of that. That's nothing and nowhere. No one wants that. Oh look, something negative, something negative. Let's just get rid of the negatives as well. And, oh, there we go. Negative's gone as well. Okay, so multiply by 2 divided through by e. We end up with 2 over e squared, and that's equal to x minus 2. So I'll add 2 on to both sides. And that's x. Now, typing this into a calculator, let's see what we get. 2 plus 2 over e, e squared. And we get 2.27-ish, which is, hey ho, looks like that's about right. Okay, but that's what we're going to keep it as for now. Let's work out the next one, which is point B, which is when x is 0 and y is something that we don't know. So now we have y minus 1 over e is equal to, and that's just going to be minus 2 times that. So both those negatives are indeed going to cancel out because that x is 0. So it's just minus e over 2 times 2. The 2 cancels out as well. So that is literally just e. So that gives us y equals e plus 1 over e. And we can check that in the calculator. So that's going to be E plus 1 over E. And on the calculator I got 3.086, which is 3.09. That's right. Okay, so this is what we've got for our triangle so far. What we want is the area of the triangle. So what you should remember from your GCSEs is that if you've got a triangle, this one just so happens to be right angled as well, you multiply this distance here by this distance there, and then you subsequently forget to half it. So just make sure you multiply this by this and half it all at the end. So distance upwards is this here, so let's just write it in. And let's go for, green's nice, E plus 1 over E all multiplied by 2 plus 2E squared. And then that's all halved for that area. One neat little trick that you could do here is to apply the half to one of these to kind of use it up. And that's what I'm going to do here. So for instance, the trick I'm kind of using is like I've got 3 things times together. So you can imagine having a 3 times 6 times a half. Now you could type that in a calculator or work it out. 3 times 6 is 18, half it you get 9. What I'm effectively doing here is saying, well, I'll use the half first. So I get 3 times 3, which is 9. So I'm going to do that half to this. So use that half up, half the 2 there, that becomes a 1, half the 2 there, that becomes a 1 as well. And the new sum is E plus 1 over E all multiplied by 1 plus 1 over E squared. Oh, not really a nice way that I can see of multiplying this out, but just doing the proper brackets, foil, smiley face, whatever you want to do. We get E to start off with. We also get a 1 over E, so that's that 1 used up. 1 over E squared times E is just going to give us a 1 over E. And 1 over E times 1 over E squared is going to give us 1 over E cubed. Oh, doesn't that look utterly hideous? Okay, E plus, well, we've got 1 over E, we've got another 1 over E, so we have 2 lots of 1 over E, so 2 over E. And a 1 over E cubed. But that's not enough. It's got to come out in this strange format here, which just seems besides the point. I mean, what? Why? This isn't... Is this not... Let's do it anyway. Okay. So if I'm adding these, I'm going to add them as if I'm adding fractions. So let's make everything over E cubed. So let's look at this first term here. If I want this to be the same thing, but over E cubed, I'll multiply by E cubed over E cubed. So that is E to the 4 over e cubed. Because if I cancel that, it becomes the same thing. Let's do the same thing with the middle part. I want this to be over e cubed. So I'll times by e squared over e squared. That gives me e squared over e cubed. And let's not forget that 2 there. And that thing's just the same. That's still 1 over e cubed. Oh my days, that is a terrible looking e. That's better. Okay, so now we have e to the power of 4 plus 2 e squared plus 1 all over e cubed. So that's it. We've worked out n. N is 3. That's all well and good. But how on earth are you supposed to go from this to this? Now it doesn't seem obvious at first, but what we actually have here is a quadratic. And this is something you can factorize. So this is actually e squared plus 1 all squared over e cubed. Now, it is quite difficult to kind of get to grips and recognize that there. So do feel free to kind of think, well, I've got an e squared, e to the 4. Why not make it e squared is equal to y? And then you have, well, this is e squared squared. So you have e squared squared plus 2 lots of e squared plus 1. So that's y squared plus 2y plus 1. Factorize that and you get this. Either way, it's a hideous question. Like, I'd have stopped here unless they'd have asked me to do anything else. This seems just as sensible as that. Oh, but either way, that's the area of the triangle OAB. Okay, question 5 of the C3 2016 paper. The function f is defined by this for all real x, and the graph of it is sketched below. Find the range of f. Now this is a very odd question, and also you should take note of how many marks this is worth. This is 5 marks for working out the range of a function. This isn't something that you can just spot straight away. There's got to be something quite in-depth here. So let's have a little look at this function again. So here we are, it's sketched like this, and it's 16x minus e to the 2x. And we want the range. Now that means we're asked to find out, is it bounded above or bounded below? Like, what's the highest thing it can get to? What's the lowest thing it can get to? And we need to write an inequality describing that. So from what I can see from this, it looks like these 2 points, well, this is just going to keep getting lower and lower. This is also going to keep getting lower and lower, a bit faster than this one over here. But it doesn't seem to be bounded below. It just keeps going lower and lower and lower. So that means the lower bound is going to be negative infinity. The upper bound, however, the highest thing that this can be is at this maximum point of the curve, which is somewhere around there. So that's what we're going to look for. That's the range. That's the solution to this range problem, is working out the maximum there. So let's work out the maximum. We have 16x minus e to the 2x. So to work out the maximum, I'm going to need the derivative, which I've called f prime of x. So I differentiate this and I get, well, 16x goes to 16. Minus e to the 2x goes to minus 2 e to the 2x by the chain rule. And they've really loved the chain rule this entire paper. You can just see every time they've tried to do a differentiation, we'll just shove the chain rule in there as well. You can practice that. So the maximum of this is when this is equal to 0. So let's work this out. So f of x evaluated at 0. So that's, sorry, f of x is, f dash of x is 0. So that's 16 minus 2e to the 2x. And it hasn't said exact, but I'm going to go with exact just because. So this lets me know that 2e to the 2x is 16. Divide both sides by 2, e to the 2x is 8. Ln both sides. Ln e 2x, well, ln and e both cancel, so that's going to be 2x. Don't know why I bothered writing the ln then. 2x equals ln 8. So x is equal to ln 8 all over 2. Also, it's possible to write this as x equals a half ln 2, sorry, ln 8 rather, ln 8, 8, 8, 8, 8, 8. And you can move that as a power. It's not going to do much with that 8, but you might get something like ln 2 root 2 or something, I don't know. That's it. So that's the highest thing that this can reach. So if that's the highest thing it can reach, then I'm allowed to say that f of x is less than or equal to ln 8 over 2. Because as we can see, if this is the highest thing it can get to, then it's bounded by this point. It can be anything less than that, and that itself, but it can't go higher than it. So that's it. The composite function f of g is defined by f of g of x is equal to 16 over x e to the 2 over x for real x, x not equal to 0. Find an expression for gg of x. That's not where I expect to see gg, but never mind. Okay, so first what I'm going to do is I'm going to look at this and look at the original function, because this is really weird. We've gone from 16x e to the 2x to 16 over x minus e to the 2 over x. So what I want to know is, what could I put here and here to get it divided by x instead? Well, what I could change x with is 1 over x. So g of x, what I've put in place of x, is actually 1 divided by x. That's where I've swapped. I've swapped this x here for 1 over x. I've swapped this x here for 1 over x. Therefore, g of x is 1 over x. So if I want gg of x, that means I put 1 over x into 1 over x. So gg of x is 1 over 1 over x. Huh. Okay, little trick for stacked fractions like this. What we've really got here is 1 divided by 1 over x. And this is actually a lot easier than it looks. All this means is 1 multiplied by the reciprocal of that. So that's the same thing as saying 1 multiplied by x over 1, which is just x. Question done. GG. C3 2016, question 6, and it just seems to get harder and harder as you go along, which is what you expect, but not really at this rate. Starting off, integration by parts on this lovely integral here. So, to start off, you are given the integration by parts formula in the booklet, which starts off by saying u dv by dx is equal to uv minus the integral of v du by dx like that. Right, so using that, we look at this part first to select u and dv by dx. Now, in general, what you should always do is select any logarithms, so the ln in this case should always be u. So this is u. And then any other function should be dv by dx. So I'm going to call this v dash, dv by dx. And just be careful with this bit here, because v dash isn't actually x squared, it's 1 over x squared, because it's on the bottom. That's ln 3x. Now, for these type of questions, if there's no logarithm, your x thing should be u, and any trig like sine, cos, tan, or any other style of function which isn't a logarithm should be dv by dx. In the hopes that the polynomial cancels itself out after you differentiate a couple of times, and the v dash is just something that you can integrate somewhere else. But let's write this out in full. So we have the integral of ln 3x multiplied by 1 over x squared dx. We have no limits, so that's a good thing. And as said before, this is u, this is v dash. So if I have u, which is ln 3x, u dash is equal to 1 over x by using the chain rule. Now, just to kind of recap, I've used this in a previous video, but we get the outside differentiated. So when you differentiate a ln, you get 1 over whatever's in the brackets. So 1 over 3x. And you multiply by the inside part differentiated. So 3. And that is 1 over x. For the Other part then, we have v dash, which is 1 over x squared, but I'm going to rewrite that as something a bit nicer. I'm going to write that as x to the power of negative 2. Now, what I don't have is v. So if I integrate this, I will get v, and that's quite important that we've got v dash. So to get to v, you need to integrate. So if I integrate this, I get add 1 to the power, divide by the new power, x to the minus 1 over minus 1. But if I'm dividing by minus 1, it's just putting a minus in front of it like that. So let's use the formula that we've got above. So it's uv minus the integral of v du by dx. And hopefully this isn't going to look hideous because of how we've chosen this to work. So we have minus x to the minus 1 ln 3x minus the integral of v u dash. So that's 1 over x multiplied by x to the minus 2. But I'm going to call it 1 over x squared for this. Oh, hang on. Sorry, it's u dash times, yeah, it's vu dash rather. There we go. So that's v u dash, and that's u dash, there's v, so we'll multiply that by minus x to the minus 1. Okay, so let's tidy this up a bit. Let's make this actually look like something that I'd be happy writing down. Minus x to the minus 1, that is minus ln 3x over x. That's that power of minus 1 coming into play. Now, in this here, I've got a minus on the outside, minus on the inside. Those are going to cancel and become positive. So I've got positive, the integral of, and this is 1 over x. X to the minus 1 is also 1 over x. So that is 1 over x squared. And what's quite nice about this is we've already integrated that before. That's minus x to the minus 1. So our answer is minus ln 3x over x minus x to the minus 1. And let's not forget our dear friend, the constant plus c. Right, so that's our integration by parts. Now we have the region bounded by the curve y equals ln 3x over x, the x-axis from third to 1, and the line x equals 1 is rotated through 2 pi radians about the x-axis to form a solid. Find the exact value of the volume of the solid generated. So what I want to do with this first off is kind of get an idea of what this looks like. So let's delete everything that I had earlier. We have y equals ln 3x over x. Which looks like that. It's rotated about the x-axis from a third to 1, and the line x equals 1. So let's just put in So x equals 1. And let's put in x equals third. Oh, would you look at that? So this part here is going to be rotated around the x-axis. So let's have a look then. If this is rotated about the x-axis, then the formula for this is pi y squared integrated with respect to x between whatever values we have here. So let's work out what we're given. We're given third and 1. So those are them. We have pi on the outside, and let's not forget to drop it. 1 third. Y squared is this thing all squared, so oh, that's dreadful. Ln 3x, and it's the whole thing squared, so I'm adding some nice square brackets there, all over x squared with respect to x. So what's interesting with this is this 2 can't be moved down to the front with a law of logarithms. It's something different to what you've seen before. If the 2 was here, right outside the 3x, then yes, it could be dropped down. However, it's actually a logarithm all squared. It's not the same thing. So this 2 can't be moved to the front. Let's work on this some more. Okay, so for this, we're going to have to use by parts again, which is torturous to say the least. We have u equals ln 3x all squared. Same reason as above, that the logarithm always has to be u, which gives us u dash, which is using the chain rule. The 2 drops down, and we get what's in the bracket here. This is now to the power of 1, so I'm going to omit that. Multiplied by the inside differentiated, well, the inside differentiated, ln 3x, just becomes 1 over x. So this is just times by 1 over x, so there we go. The next part then is v dash being integrated to get me v. Now v dash, same as before, there's an x squared on the bottom, so that's 1 over x squared. And our integral for that is negative x to the negative 1. Oh boy, let's integrate this. So it's uv, so that's ln of 3x all squared. Let's put the negative on the outside and the x on the bottom for that. Same as before, this is x to the minus 1, so that's 1 over x, and there's a negative, so I've just rearranged it to look like that. Minus the integral of v u dash, so that's minus x to the minus 1, and we've got u dash here, which is 2. Oh, horrible. Absolutely horrible. And just for good measure, I'm going to chuck in all the limits before someone else in the maths department yells at me saying, "You're not doing it right, Josh. You're omitting limits." Okay, so we can tidy this up a fair bit. What we can do is we can say, well, minus x to the minus 1, well, there's a minus here, minus there, so that's going to give us a plus. We've got x to the minus 1, x on the bottom, that's going to give us over x squared. We've got 2 ln 3x. This 2 is just a constant. I can move this outside. And we get ln 3x here. With respect to x, here's my third on the bottom. Here's my 1. And because I am exceedingly lazy, there we go. Right. Okay, so we've got this with limits. We can literally sub that into a calculator. And we also have this here, which looks alarmingly similar to something we've seen before. We actually know what the answer to this is. We just made it. We've got it here. So we can put that straight in place of that. So we have minus ln 3x, and I should have copy-pasted this again. I don't know why I didn't. All squared over x between 1 and a third plus 2 lots of the thing we got from our last answer, which I am indeed going to copy-paste. And, oh, I'll get rid of that plus c, we don't need it, this is a definite integral. There we go. That's it. This is also between 1 and a third. Okay, now that I've done this, I can pretty much just sub in these numbers to get an answer. But it's asking for the exact volume, so omit that, I cannot. So let's go about getting this in exact format. So we're going to have 1 subbed into this, so we have minus ln 3 all squared over 1. Minus, when we sub a third into it, minus ln 3 times a third all squared over a third, plus 2 lots of this thing with the same thing subbed in. Oh god, this is tedious. Minus ln 3 over 1 minus 1 minus the same thing when a third is subbed in. So ln of 3 times a third over a third minus third to the power of minus 1 is 3. Oh, how super delightful is this? So let's start cancelling some things off. So first off, 3 times the third is 1. Ln of 1 is 0, so that gets obliterated. Oh, so glad to see that go. Same thing happens here. That bit gets obliterated as well. And then we can start tidying this up a bit more. Divide by 1 doesn't matter, so we've got negative ln 3 all squared plus 2 lots of negative ln 3, so that's going to be minus 2 lots of ln 3. And that's going to be minus 2, but then we're going to have minus times 2, so that's going to be positive 6. So that gets us 4 minus ln 3 all squared minus 2 ln 3. And that looks pretty close to the final answer. However, it isn't, because all through this, I've forgotten this guy. Whenever you're doing a volumes of revolution, don't forget to have the pi. So at the end of this, I could then say, therefore, the answer to this is pi multiplied by, no, it's not letting me take that. I'll have to write it out in full. 4 minus ln 3 all squared minus 2 ln 3. And that's it. That's our answer. Okay, so this is question 7 of the C3 2016 paper, and by now I'm just getting a little bit fed up and tired. But let's go on. 7a, by writing sec x as cos x all to the power of minus 1, use the chain rule to show that if y is sec x, then the derivative is sec x tan x. Now, just a quick note about this. This is definitely not the same as inverse cos, like that. They're not the same thing. I mean, you can check the graphs if you like as well. Sec x and that aren't the same, which might get a bit confusing later on, but that's fine. We'll go through it. So to start off with then, we want to use the chain rule on this to show that the derivative is that. So y is equal to reciprocal of cos x, like that, or sec x. If we take the derivative, that is y prime, then this is a chain rule. So it's minus 1 drops down to the front, times by the power, take 1 from the power is the rule. And now we multiply by the inside part, this bit differentiated, which is now negative sine x. Okay, I've written it in brackets because of that negative there. I want to make sure I'm not confusing myself by taking it away or anything. So the minuses here are going to cancel, and we end up with sine x over cos x all squared. Now, confusingly enough, cos x all squared is the same as cos squared x, which is really annoying in a lot of ways, because I just said that that wasn't true for this up here. But this is just some mathematical historical mess up of the most grand kind. Let's just put it that way. Yeah. So let's think of another way of writing this so we can actually get sec x tan x. Well, luckily enough, we can rewrite this as sine x over cos x cos x, because that is what cos squared x is cos x times cos x. Now I'm going to borrow a invisible 1 here. This is sine x times 1 over cos x times cos x. It's exactly the same thing as I had before. And this allows me to really see how this comes about now. Well, we've got sine x over cos x, which is tan x. And we have 1 over cos x, which is sec x, which is pretty much what they've got there. I'm not going to be pedantic enough to rewrite that, but that's it. That is what we have. So now we've got part B. The function f is defined by f of x equals blah blah blah. Find the value of the y-coordinate of the stationary point of the graph of y equals fx, giving your answer in the form p root q, where p and q are integers. So we want the stationary point of this. So for a stationary point, f dash of x is equal to 0. So let's differentiate that to get f dash of x. If I differentiate tan x, I get sec squared x, and that comes from the formula booklet. Now I've got a 2 in front of it, so it's 2 sec squared x. If I differentiate this, well, luckily enough, I know what that is when I differentiate it. I'm told that differentiating sec x is sec x tan x. So I can just write that as minus 3 sec x tan x. And then this must be equal to 0. So if this is equal to 0, I get 2 sec squared x minus 3 sec x tan x is 0. Now, at this point, you may be thinking, oh, I want to use one of my fancy new trig functions. I want sec squared to change into tan squared x and plus or minus 1 or something or other. And then you end up in basically the same position because you've still got a sec x and a tan x, and it doesn't seem like there's much to do. One of the nice routes you can do with this is to factorize out a sec x, and that's what I'm going to do here. Let's take out sec x, which gives me 2 sec x minus 3 tan x equals 0. So now I have either sec x is 0 or 2 sec x minus 3 tan x is 0. Now, what I'm going to do is I'm just going to check what the graph of sec x looks like, and this is it. This is the graph of sec x. Now, sec x can never be 0. There it is. There's the line y equals 0, and that's sec x not ever reaching it. So, this thing can't be 0. This is what's left. This bit must be 0. This we can just ignore from now on. So, 2 sec x minus 3 tan x equals 0. Okay, so rewriting this out a bit more, we get 2 1 over cos x minus 3 sine x over cos x, and you might be able to see where I'm going with this now, equals 0. We've got something positive, something negative, equals 0. Let's put them equal to each other. So now what we've got is cos x divided on both sides. So let's multiply everything by cos x, and we end up with 2 equals 3 sine x. You can just cancel those cos x's out by multiplying both sides by cos x. So 2 over 3 is sine x. Now in the calculator this doesn't give you anything special when you work out x, but the one thing you need to be very, very, very careful of is that when you want inverse sine of 2/3, you have to be in radians. There's a big clue at the top here, radians. Look at that pi. Instant hint for radians. So 2/3 is equal to sine x. That is the location of stationary point when x is equal to 0.7297, the rest of it. So how does that help us here? So I know what sine x is. It's 2/3. I wonder what the other things are. If sine x is 2/3, then looking at a triangle, SOHCAHTOA, opposite over hypotenuse. So the opposite is 2, the hypotenuse is 3. This part here, well, 3 squared minus 2 squared is 5, so this must be root 5 down here. It's 9 take away 4 and rooted. So that's that there. So I could quite happily work out what cos x is. Cos x is the adjacent over the hypotenuse, so it's root 5 over 3. And then tan x is equal to the opposite over the hypotenuse, so that's opposite over the adjacent, 2 over root 5. Lovely. Just another quick thing on this. It's a good idea to check what signs these should be as well. Now, in this case, they end up both being positive. I'm just going to show you quickly as to why. We've got the cast diagram to help us. Now, cast isn't a great way to remember this because it doesn't actually start with C. But I'll just explain how this works. So this is a cast diagram. What this is for is this is a quick way to work out whether a trig function is positive or negative if you know what two values it's between. Now this one is set up in degrees. I'm going to write it in radians as well. There we go. Right. So what this does, and I can write this all here, I'm going to write in y equals sine x, y equals cos x, and y equals tan x. So those are my three graphs here. I'm going to zoom in and just particularly want to look at between 0 and roughly 2 pi, which is 6.3, well, 6.2 something-ish. Okay. I'm going to put in pi over 2. Oh, hang on. Doesn't like that. Sorry. X equals pi over 2. X equals pi, and x equals 3 over 2 pi. Those are my three lines. And these sections are the cast diagram. between 0 and pi over 2, so between 0 and 90 degrees, every single one of these trig functions, tan in red here, cos in green, and sine in luxurious brown, they are all positive. Look at them all positive, all above the x-axis there. And then between pi over 2 and pi, so between 90 and 180 degrees, only sine is positive. Look at it. It's the only brown one, it's the only positive one. Cos is negative, tan is negative, sine is positive. Between pi and 3 over 2 pi, or 180 and 270, only tan is positive. And then between 3 over 2 pi and pi, only cos is positive. That's what's summarized here. So, go away. We've been told that x is between 0 and pi over 2. So, between 0 and pi over 2, all of the trig functions are positive. These are both positive. I don't have to worry about the signs of these, they're positive. Right. That's a bit of a side note, but we can go back to answering the question now, the y coordinate. So this is f of x. We want the y coordinate of the stationary point. Well, that's going to be quite easy now. We're told that it's 2 tan x minus 3 sec x. Well, that's all well and good because we know that tan x is 2 over root 5. So that's 4 over root 5. 3 sec x, well that's 3 lots of 1 over cos x. So that is 3 times 3 is 9 over root 5. So that is now going to be minus 5 over root 5. So what we can do now is multiply this by root 5 over root 5. And we get minus 5 root 5 over root 5, sorry, over 5, because root 5 times root 5 is 5, which is minus root 5. And just looking at the mark scheme quickly, there we have it. That's it. Okay, so now we're on to question 8 of the Core 3 2016 paper, and it's the dreaded integration by substitution question. And I don't know why it's so dreaded, because it's the most formulaic question that you will get on this entire paper. It is always the same steps every single time, and as long as you know what you're doing and you're fine and happy with your indices, these questions can pose no threat. So, it's told us u is equal to 4x minus 1, and this is our integral between a quarter and a half. So, let's go for it. Start off, look at your substitution, u equals 4x minus 1, and we're going to differentiate it. Every single time, this is what you do. So du by dx is equal to 4. Now, next step is I want to get dx on its own from this here. So, if I want dx on its own, what I'm going to do is multiply both sides by dx and then divide by 4. I urge you very, very strongly to always do this calculation, because if there's anything with a trig function, people get very messed up very quickly if they just learn by rote, oh, you just switch them around. Just be careful, multiply by dx, divide by 4, and we get that dx equals du over 4, or quarter du. Either one of those is fine. Okay, now we can deal with this integral. So we've got the integral of a half, and this is an x limit, so this is, I'm going to put these equal to x, and a quarter of 5 minus 2x and this is now u to the power of a third du over 4. Okay, so at this stage, if this was a nice integral by substitution, what would happen is that we'd get some function of x here which would conveniently cancel this one out, and we'd have an integral strictly in terms of u. However, in this case, that hasn't happened. So because that hasn't happened, I now resort to looking at this and changing this to an x equals function. I only do this if it hasn't cancelled out anything here. Cannot stress that enough. I only do this if a cancellation hasn't occurred and I've not got everything in terms of u. So what I now have is u plus 1 divided by 4 is x. Now I can use this. So let's have a bit of a go here. I've got, these are still x limits. And now I'm going to sub this in, so I've got 5 minus 2 lots of u plus 1 over 4, u to the third du over 4. Right, everything's in terms of u. What I'd like to do now is change the x limits to u and then deal with this over 4 here, because this seems to confuse a lot of people. So in terms of x limits, what I'm going to do is I'm going to sub a quarter and a half into this here to get some new limits. So u equals 4 times a half is 2, so 2 take away 1 is 1, and u equals, if I put a quarter into that, it's 1 minus 1, which is 0. Oh, how lovely is that? So those are the new limits, 1 and 0. Just a quick note as well, the order is preserved. I put half in, I got 1, so 1 is on the top. I put a quarter in, I got 0, 0 is on the bottom. Sometimes you can end up with a higher one on the top than on the bottom, and that happens, it works, it's fine, looks weird, still works, just deal with it. Okay, this 4 here, everything is being multiplied. I'm just going to take this 4 outside, so I've now got a quarter outside of everything. And now I'm going to open up this bracket, so I've got 5 u to the third minus, and that's going to be 2 u to the third u plus 1 over 4 du. Let's do some more bracketeering. Quarter 1 0 5 u third. Open up this bracket. Everything's divided by 4, so that's going to be this 2 and this 4 mean that everything is going to be halved instead. So that's half u to the third. So it's this times this, which is going to be u to the 4 over 3. And then u to the, well, it's going to be minus a half u to the third du, which is the same thing as the integral of 0, 1, 5u to the third minus half u to the third, that's 9 over 2, let's not forget this quarter, 9 over 2 because 5 take away half, u to the third minus a half u to the 4 over 3 du. Now I could take out even more stuff if I wanted to, and I think I probably will, just to make this easier on myself in the long run. I'm going to take out these 2's because I'm halving everything in this. So if I take out these 2's, I'm going to get an 1/8 on the outside. 0, 1, 9u to the third minus u to the 4/3 du. And this is the nicest thing that I'm going to get for this. So let's just integrate it. So I get an 1/8 on the outside, some lovely square brackets. This integrated, add 1 to the power, divide by the new power, so that's 4/3. So that's going to be 27 over 4 u to the 4/3 minus, and add 1 to the power, excuse me, gets you 7/3, so that's 3 over 7 u to the 7 over 3, 1, 0. So in this one, it's really quite nice with this 0. If I sub 0 in, I will get 0. There's no exponentials, there's no causes, so that's all well and good. Okay, so I just need to sub in 1. So I end up with an 1/8 times 27 over 4 minus 3/7. And what's really quite nice about this is I can just put this all into my calculator, and I should, emphasis on the should, get a rather nice fraction as a result. Well, I say rather nice, I'm yet to be convinced by my calculator. 177 over 224. And if we have a look, that is what the mark scheme reckons we should get. Okay, so this is the Core 3 2016 paper, question 9. And it's obviously a trig question, but it's not the standard one that you'd expect on Core 3. Now, The standard question that you want is a sec squared plus a tan squared, or minus 3 sec is 4. That style of question that you can use one of your new fancy trig identities, such as tan squared x plus 1 is sec squared x, to solve it and get some solutions by making this quadratic. This isn't one of those type of questions. This is a bit weirder. What's particularly different with this question is that even if you've done all of the past papers and practiced all of the trig stuff, you may still not be able to answer this question very well, because the techniques, you probably wouldn't have seen them in any other paper. So these are standard techniques, but I'll go through how they're used and how you can answer this question effectively. So first off, you're told sec x minus tan x is -5, so show that this is also true. You may be thinking, well, I know an identity using sec and tan, well, both of them squared, that is, and that is tan squared x plus 1 is sec squared x. Now you can either learn that by rote, or you can derive it from the sine squared plus cos squared equals 1 by dividing through by cos squared. That tends to be what I do most of the time, because it just means I've got less things to remember in my head. Right, so we can't actually use this because there's no sec squared or tan squared. And if I wanted to make one, I can't individually square things because that's a big no-no. But I could square both sides. And if I did that, I'd end up with a large quadratic here, and it's got tan squared, sec squared, it's also got linear tan sec terms. Not going to be much use at all. So there is a trick. I look at this -5 and I work out how it's related to -0.2. That is, it is the same as -1/5. So you might think then, well, how do I get this to be -1/5? I flip the entire thing. So that is 1 over sec x minus tan x is -0.2. And that's true. But where do you go from there? There's nothing really strictly obvious that you can do now. Well, this is the trick that we're going to use. First off, I'm just going to call this S and this here T for the next part. So 1 over S minus T. And what I want to do is make that S plus T. I'm going to multiply this by 1. It's not just any one, it's a special chosen one. I'm going to multiply it by S plus T over S plus T. And again, this isn't a technique that you will generally see in an A-level question. It's something that comes with mathematical experience and things. So don't be alarmed if you didn't see this straight away. I don't know how AQA could expect you to see this straight away, especially at the end of this whole paper, which was long in itself. So 1 times S plus T is S plus T. S minus T times S plus T, well, we're going to get an S squared. We are going to get minus T times S, and we're also going to get S times T. And those two will cancel each other out. The last term we have is minus T times T, which is minus T squared. Now, just recall This is sec squared x. This is minus tan squared x. So, funnily enough, we can actually get rid of this bottom because sec squared x minus tan squared x is 1, just by rearranging this identity up here. So that is sec x plus tan x over sec squared x minus tan squared x is negative 0.2, and this just cancels down to give 1. So that is it. Sec x plus tan x is negative 0.2. So that's the first question done. The second one is, again, quite strange. I mean, you're told sec x and tan x in two different equations, hence find the exact value of cos x. Well, which equation do you use? Do you use the top one and change it into sines and cosines and try and work your way from there? Do you use the bottom one because that's the new one that they've given you? Is it going to be somehow easier because they've given it to you? It turns out you don't use either one, you use both. And the trick is to add them together. So we have sec x minus tan x is negative 5. Sec x plus tan x is negative 0.2. And as I just said, we'll add these two together. And we get 2 lots of sec x minus tan x plus tan x. That goes away, it's gone. And we end up with negative 5.2. You can type this into your calculator to change this into a fraction because it's nicer to work with later on, but I'll do that in just a moment. We have then sec x, by dividing both sides by 2, is negative 2.6. And as I said, I want to change this into a fraction, so that is negative 226 over 10, which is minus 13 over 5. So that means that sec x is minus 13 over 5. And sec x is 1 over cos x. So finally, that means that if we flip both fractions, cos x is negative 5/13. Job done. So the final question now is not impossible, but it's interesting because this is where AQA make a mistake, and I'll point it out in just a moment. So starts off with saying, hence solve the equation sec 2x minus 70 degrees minus tan 2x minus 70 degrees equals negative 5, giving all values of x to one decimal place in the interval negative 90 degrees to 90 degrees. And if I've said degrees too many times, it's only because I'm drawing emphasis on that your calculator should be set into degrees for this question. So the mistake in this is giving all values of x. Emphasis on that there, because that means that it's going to be plural. And there's not two solutions to this in this interval. There's only one. AQA have got this wrong. So, just to kind of illustrate the point further, this is the graph of this here. Now, currently this one is put into radians for this, and it's 1.57 for half pi, negative 1.57 over here, which is negative half pi, so 90 degrees, 90 degrees. Here is the one solution there that we're looking for. There are no other solutions. Now this graph may be off to scale or what have you, but there is only one solution within the interval. Okay, so now that we have this here, well, we've got this interval as well. This here, I'm going to rewrite it as sec theta, where theta is 2x minus 70, minus tan theta is minus 5. So that's exactly what we've got up here. And from this here, we worked out that this is true. And from both of these, we worked out that this is true. So what I could say then from this is that cos 2x minus 70 is negative 5/13. Now, what I'm going to do here is a core 2 technique, which is to use a helper variable to work out the range for this graph, because it's not going to be between 90 and minus 90 if we use a helper variable and solve for it. The reason it's a good idea to use a helper variable is because of this transformation here, this stretch scale factor of a half in the x direction. So let's just adjust the range accordingly. So I'm going to say cos of theta is negative 5/13. We have our range, which is minus 90 to x to 90. Let's work that out in terms of theta. Well, theta is 2x minus 70, and that must mean that x equals theta plus 70 all divided by 2. And I can plug that into there, so minus 90 to theta plus 70 over 2 to 90, and adjust the range. Multiply both sides by 2, and then take 70 away from both. So that's minus 180 minus 70, which is minus 260, is it? Oh, I think I made a mistake. Minus 90 times by 2, minus 70, oops, 250. Oops, it's too early for doing this. (250) to theta, and let's see if I can do my arithmetic properly this time. 180 minus 70, 110. Sounds about right. Okay, so the solutions for this are now going to be inverse cos of negative 5/13, making sure that you're in degrees, and it gives you that. So theta is that from the calculator. The next solution that we get is 360 minus the first. So I type in my calculator 360 minus ants, and I get 247.38. Now, neither of these solutions are in range for theta, so I need to adjust these accordingly now. So I'll take 360 away from this one, because taking 360 from this isn't going to get me anything worthwhile, I don't think. We'll try it both anyway. So 112.62 minus 360. Oh, it seems that I was wrong. This is going to be in range. We get minus 247.08. And this next one, 247.38 minus 360, and we get negative 112.62. Excellent. So now that we've got these, we need to write these in terms of x. So theta 2x minus 70. So that means that minus 247.08 is 2x minus 70. And also minus 112.62 is equal to 2x minus 70. Rearranging for x, this gives me two values for our answer. So that is plus 70 divided by 2, negative 21.31. Our next one, negative 247.08 is, oh, that may have been written down incorrectly there. Yes, I think I have 112 minus, well, 0.62 minus 360. That should be 3. Forgive me for that sloppy error there. So 247.38 plus 70 divided by 2, and we get the other answer that's in the range, negative 88.69. Right, these are both within the range negative 90 to 90. So are they both right? Well, check them. You can sub this into the original expression that we got. That is this up here, and it doesn't work. It's not right. It doesn't solve it. In fact, I believe it gives you a solution to this equation up here, not for this one. This solution, 21 minus 21.31, does in fact work for this here. And because we've used both of these formulas to derive this here, it's not implied both ways that this solution works. So this from AQA is a mistake. They didn't go far enough to see that one of these solutions wouldn't work until the mark scheme was released, and they put it here saying, yeah, some students will write this down, but it is not a solution to the question asked. And that's it. That's the C3 2016 paper.